This is section 2.3, part C. When we're given real-world data, most of the time the fit isn't precise. We don't have exactly data that's linear or quadratic or exponential. But what we can do is look at our data and decide which model it seems closest to. That's what we'll be looking at in this section. So when I give you a set of data, like here, what we're going to do is, at least for right now, I'm going to restrict us to choosing between a linear model and an exponential one. Those are the only two choices we have for the moment. Usually the most effective way of deciding what we have is to go ahead. We're going to have to put the data in the calculator anyway. If we simply plot it, it'll be pretty quick to determine whether it looks more like a straight line or more like an exponential growth or decay curve. So let's do that. The data we have here is for the federal debt for various years, and I'd like to predict the debt in 2020. We've seen before that it's usually not effective to put big numbers like years into our equation, so let's just pick a starting year. Let's go ahead and we'll say T is years after, and I'm going to choose 1960, since that's the first year in the table. So I'd have 0 and 10, 20 and 30, 40, 45, 50, and 56 for my T values. So we go to Stat in the calculator. And we do want to edit, so I'm just going to hit Enter. And we'll clear out any data that's already in our lists. And put in, first of all, our first column will be the T values. In our second column, we'll put the debt, which is in billions of dollars. And I do want to plot that data. So in my window, my years go from 0 to 56. So if I went from 0 to 60, that would cover those, and I'm just going to count by tens. The Y values are the debt. Let's go 0 to 20,000 would cover that. And I'll count by thousands on that axis. In my Y equals, I'm going to clear out my old equation. I don't need that anymore. And I'm going to turn the plot on just by highlighting it and hitting Enter. And then I'm ready to graph. Looking at that picture, you can definitely see the exponential growth curve here. It's certainly not a straight line. We can see that curve that we've been associating with exponential functions this chapter. So let's go with an exponential model. As we've done before, when we have data that isn't a perfect fit, the way to get the best possible fit is by using regression on your calculator. So if you go back to Stat, and this time Calculate, you have to go down a little ways. It's actually the 10th option. You'll find EXP for Exponential Regression. And I'll go ahead and pick that. Looks good. My X and Y are in list 1 and list 2. So I just want to calculate. And there we go. Same formula we've been using, the A and the B. And they give me A is 228.65. B is 1.0834235, let's say. And by the way, there's those correlation coefficients again, the R squared of 0.986. Really good, very close to 1. So, exponential y equals AB to the x. The y value is the debt. I'm going to call that D. And let's see, A was the 228.65. B is that big long number there. And the x values are the t's. So there's my model. Our goal was to predict the debt in 2020. So in 2020, that would be 60 years after 1960. So D of 60. And if I just do that in my calculator, I'm just going to round off to the nearest whole number because that's what they've done in the chart here. That is in billions of dollars. So what, almost 28 trillion is what we're looking at there? Would be the predicted debt in 2020. All right, let's take a look at the next one. This one we've got a world population problem. We've got various years again in the population of the world in billions. Let's go ahead and for our t values, I like to use whatever's beginning of the table usually. So I'm going to go years after 1950 for my t. So we've got 0, 20, 30, 40, 50, and 58. So same deal. Back into stat again and edit, and let's put our new data in. There we go. All right. I need to decide what kind of model I'm going to use. So again, in the y equals, I still don't have an equation in there. The plot's turned on. That's all good. In my window, it looks like 0 to 60 is still a good x window. But on the y's, I have much smaller numbers this time. Let's go 0 to 10 with a scale of 1. And this time, as I look at that graph, it looks very much like the data is in a straight line. So I'm going to choose to do a linear model this time. This will be review since we did linear way back in the preview chapter, the preliminary work. So let's go ahead. In stat again. Calculate. We want that linear regression. Y equals mx plus b. Our y value is population, so I'm going to call that p. The slope, the calculator actually calls it a, but we know that's our slope. So 0.0737 times x, which is the t value, plus b, 2.3565. I keep 4 decimal places here. Again, a really good R-squared, almost 1, so excellent correlation coefficient. So there's our model. And if we want to see what the population prediction for this year would be, 2018, which is when I'm making this video. It may not be when you're watching it, but at least for right now, I'm going to use 2018. You can adjust as needed. Let's see where we're going. After 1950, so that would be a t of 68. So if we plug 68 in for the t, I'm getting 7 point, I guess they're keeping 3 decimal places in the chart, so I'll be consistent, 7.368 billion. Would be the prediction. All right, I think I'm going to pause there. These are a little more time-consuming. Let's pause there, and I'll do one more section for the last page of the notes in this section.